Alright, so we're going to revisit differentiability today. Before, you learned that a differentiable function, or a function is differentiable when the function is continuous and smooth. And smooth is a very loose term, right? Because it's talking about, not having a sharp turn in it. But even then, you would have to get in very, very close in order to really see if a function has a curve in it. And so the way that we're going to deal with this situation is by first checking for continuity, because continuity is super important with differentiability. If it's not continuous, then it's automatically not differentiable and you can stop. You don't have to keep going. But when we're talking about differentiability alone, like the smooth curve, we're going to see if the derivative from the left is actually the same as the derivative from the right. So we're going to find the limit of the derivative from the left and from the right, because then if they're the same, because you're talking about a slope, then those values will indicate whether or not the curve is smooth. So the way we're going to do this, so we're just going to jump right in. First, in order to determine if a function is continuous, differentiable, or neither, the first thing we have to test is continuity. So we do that by finding the limit as x approaches 5 from the left of f of x, and setting it equal to the limit as x approaches 5 from the right of f of x. And we should pay attention to the function, because the function says that x is less than 5 for this bottom equation. So that means we have 5 times 5 minus 19. And we're trying to see, well, and I put a question mark here, because I don't actually know if they're the same. I need to prove that they're the same or not. So that needs to possibly equal 5 squared minus 5 times 5 plus 6. Okay, and then when we do this and we plug it into our brains, because we are capable of doing this problem in our heads, 25 minus 19 is 6, and 5 squared minus 5 times 5 is 0, so this adds up to 6 as well. But that's only one of the requirements, so that says that the limit exists. Now we have to come back over here and we have to be like, well, what is f of 5? In order to find f of 5, you need to look at the function, and you're looking at where it is or equal to. And then because we took the limit over there, and we got 6, that value is going to be 6. Now, so that's the second requirement. The third requirement is that the limit, as x approaches 5, of f of x equals f of 5. Well, is that true? Yes, because all this work in the middle says that the limit is 6, and f of 5 is 6, so that satisfies all three requirements. So this is at least, if nothing else, continuous. Now we need to determine if the function is differentiable. So in order to determine if the function is differentiable, we need to take the derivative. So we're going to take the derivative of f of x. So let's say f prime of x. And the way that we're going to do this is by taking the derivative of each piece of the function. So the derivative of x squared minus 5x plus 6 is 2x minus 5. And that's where x is greater than or equal to 5. Nothing changes with the domain for that part of the problem. And then 5x minus 19, the derivative of that is just 5, for x is less than 5. Now we need to see, well, is the function going to be, is it really differentiable? And the only way to know is to find the limit as x approaches 5 from the left of f prime of x, and seeing if the limit as x approaches 5 from the right of f prime of x is equal to that value. So when we're going from the left, we're talking about this lower function here, which is 5, right? Because no matter what you plug into 5, you always get 5, because there's nothing actually to plug it into. And then 2 times 5 is 10 minus 5 is 5. So that is also true. But let's keep going, right? So is f prime of 5 equal to 5? Yes, and we know that because that, again, is this top function here, so that is 5. And the limit, as x approaches 5, of f of x is 5, is f of 5. Right, they do have the same values. So again, that is true, right? Just like the continuity was true. So this is continuous and differentiable. And I'm going to abbreviate that with a DIFFBLE. Okay, so this function is continuous and differentiable. All right, let's do part B. Well, first we need to check continuity. So we take the limit. We find the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. And the reason that I really focus on these 3's is because if you look at both of these functions, they're all polynomials. So they're all going to be differentiable everywhere, continuous everywhere, except possibly where it switches from one equation to the other, right? That's why we test those numbers as opposed to everything else. So please keep in mind, if you have a rational function or something where you might not be able to plug in a number such as a square root function, then that affects whether or not the function is continuous. So please pay attention to that, because it is possible that even if it is continuous at the value you're looking at, it might not be continuous everywhere. So we're going to take 3 and plug it in. So we get on the left 17 times 3 minus 9. And on the right we get 3 squared plus 13 times 3 minus 5. And then when you plug that into your calculator, you get, no, I don't have it figured out yet. $42 on the left, and then 13 times 3 plus 9 minus 5 is 43. And 42, and remember these were question marks, right? We didn't actually know. 42 does not in fact equal 43, which means this is neither. Okay, because remember, as soon as you determine that the function is not continuous, it therefore is not differentiable either. Okay, it can be continuous but not differentiable. It can be continuous and differentiable, but it cannot be differentiable when it is not first continuous.